Okay, I'm going to start the recording.
Todo molesta.
Okay, so I think we can start already. You can share your screen, Tim.
Okay.
Okay, so thank you very much for being here. Let me introduce you to Tim O'Brien, who did his PhD in Manchester and working in several places in the UK. And then he came back to Manchester in 99, but in a different place where he did his PhD. He's now in the Jodrell Bank Center for Astrophysics. And he has been working in novae, both in observations and also in simulations. And today he's going to talk us about his favorite star. 38 years and 3 explosions of the recurrent nova, RS Ophiuchi. So whenever you want, Tim, it's all yours.
Okay, thank you very much. So thanks for inviting me. It's lovely to give a seminar. And if there was one thing that came out of COVID that might be a positive, then the sort of having more online seminars where you can invite people from around the world is probably one of those things. I want to talk about my favorite star, I guess, and the reason is because as we'll hear, I actually did my PhD on studying this star way back, starting in 1985, and I've since been able to had the good fortune to be able to continue to study it off and on for the last sort of 4 decades, I guess. And so you'd hope we'd learnt something about it. So we have learnt a little bit, and I hope to explain a bit about that for you. And I just thought I'd show you one of my best observations here at the beginning, which is just a handheld mobile phone picture from when it had its most recent outburst, when it became bright enough to just take a picture of it in the night sky in August of 2021. So let me tell you what this is. First of all, it's what's called a recurrent nova, and they are binary star systems. So there's 2 stars orbiting one another. In this case, one of the stars is a red giant, and the other star is a white dwarf, and they're separated by of order the distance between the Earth and the Sun. And what happens is there's such a close binary that the red giant either fills its Roche lobe and material overflows onto the white dwarf, or some proportion of that material might be intercepted from the wind of the red giant, but effectively there's an accretion process from the red giant onto the white dwarf. Material builds up on the surface of the white dwarf until eventually the pressure reaches a sort of critical point at which you start thermonuclear reactions, so hydrogen fusion reactions in the accreted material at the base of this accreted layer. At that point, because the material is degenerate, then there isn't a sort of safety valve, so this thing runs away very rapidly, and you get a thermonuclear explosion. So there's a huge explosion covering, we think, pretty much the whole of the white dwarf. That's still studied, the details of that, but that results in material being ejected at very high speeds, thousands of kilometers per second. And in the case of something like RS Oph, where there's a red giant, the ejected material will crash into the wind of the red giant, and it sets up a shock system that produces extremely hot gas at millions of degrees, that can accelerate particles and produce emission. And so you effectively get sort of interesting radiation across the electromagnetic spectrum. Now, one of the things about recurrent novae is that the white dwarf isn't destroyed. fact, novae in general. The white dwarf isn't destroyed in that explosion. And so once the eruption has died down, the accretion process can begin again. And at some point later, you can have another explosion. Now, there are many novae systems, which are basically these white dwarf binary systems where you get these sorts of eruptions. But for the majority of them, we think the time scale, the time between explosions is probably measured in hundreds of, well, many thousands of years. And so we only ever see one eruption. For the recurrent novae, we're on the end of a distribution where we get to see on human timescales, we get to see more than one explosion. So in the case of RS Oph, we're getting explosions roughly every sort of 10 to 20 years. We think that that's because the white dwarfs in these systems are on the massive end of the scale. So they're approaching the Chandrasekhar limit of 1.4 solar masses. And so they reach this critical pressure more quickly than other less massive white dwarf systems. So that makes them interesting for other reasons, because that makes them potential type 1a supernova progenitors, for example. If the white dwarf were to reach that critical mass limit, then it would explode as a type 1a supernova. So as I say, plenty of physics processes occurring in these systems, all the way from accretion in binary star systems to thermonuclear processes, nuclear synthesis of various isotopes, shocks, particle acceleration, etc., etc. Lots of things going on, and often, happening in real time as we observe it. I mentioned the potential type 1a supernova progenitor, and I think one of the interesting things about seeing these things happen reoccur on timescales of, say, 15 to 20 years, when you get another outburst, your telescope instrumentation and technology has changed significantly on that sort of timescale. And so when the next outburst occurs, you actually have a chance to re-observe it with far better technology than you had before. And therefore, it's an interesting experiment in a way, that you can get to see it happen again, test your ideas from the previous outburst, see things in more detail and in different ways. And just a picture on the side there is just an aside, really, which shows you the most rapidly recurring recurrent nova. That goes off about every autumn, pretty much every year, and it's in the Andromeda galaxy. So that's the most rapidly recurring recurrent nova we're aware of. So potentially the one that's closest to the Chandrasekhar limit. This is the light curve for RS Oph. So this is from the AAVSO, the American Association of Variable Star Observers. And this goes back to the 1930s at the left-hand edge of the diagram. And at the right-hand edge, we're up to more or less the present day. And you see these very obvious outbursts where the thing brightens from a sort of quiescent magnitude of around 11. This is a visual magnitude. Mainly that light's being contributed by the red giant. But then at the outburst, you get this very rapid rise and then fall in brightness. There was another outburst that we're aware of in 1898, and there almost certainly were more in the past, going back potentially thousands of years, but they weren't noticed until 1898. There's discussion of whether some have been missed in here, maybe one in here around the time of the Second World War, for example. People might have been distracted around that time, so maybe they missed an outburst, but people discuss these sorts of things. But typically 10 to 20 years sort of inter-outburst times. This is a zoom in to the same data set. This is V-band optical light curve of RS Oph from the most recent outburst in 2021. And you see the sort of system burbling along here, and then very rapidly rises and then decays away on the timescale of a few months. The gap is just because the nova becomes too close to the sun to observe there in the visible. We know that in these outbursts, there is mass ejected, and you can see that in spectroscopy. I mean, this is just one example. There's many similar observations of this and other novae, but you see this. This is the H alpha line, in the optical part of the spectrum. And what you see here is this sort of broad structure from this outflowing material, so Doppler shifted into this broad line with a P Cygni absorption in the material coming towards us, showing you the sort of extreme velocities that you can get. And this, in this case, 5,000, 6,000 kilometers per second. And there's also a sort of very narrow feature here, which is interesting, with its own little P Cygni absorption. And that's emission from the wind of the red giant. So outside of this expanding material from the explosion, you've got this almost stationary, 15, 20 kilometers per second, slow red giant wind that the ejection's running into. And here this has been lit up, it's been illuminated by the explosion. And you can see the evidence for that there. And of course, if you look at these things in much later, after the outburst, then you can see the sort of nebula remnants. So you can see the stuff expanding out from these systems. And these are old novae. This is H.R. Dell had an explosion in 1967. DQR was 1934. GKP was 1901. And this V1500 SIG was 1975. So you can see this stuff's ejected and it is visible at quite late stages. However, these are all so-called classical novae where we've only seen one explosion of this type, whereas for the recurrent novae, where we see more than one on a human lifetime, we think there's probably less mass ejected. The explosions happen so often that perhaps isn't as much material accreted. There isn't as much stuff ejected, and so they're not as obvious as this for long timescales. Sort of moving on from the optical to radio and X-ray observations. If I went back to 1967, I would find no radio or X-ray observations of this object we're interested in, my favorite star, RS Oph, because the first time we ever made any radio observations were back in 1970, and the first X-ray detection of a nova was not till the 1980s. So broadening things beyond the optical wave band was within the last 50 years rather than something that's been done for 100 years or more. So if we get to 1985, then sort of my interest in this object begins. There was an explosion on February, or we saw it, the explosion on February the 26th. It's about 9,000 light years away, so it took place 8,000 to 9,000 years before that. And it was when I began my work with Franz Kahn and Mike Bode in Manchester, and the idea was to develop a model for the expanding remnant of the explosion. And so we made quite a lot of use of X-ray observations at that time. In 1985, all we had was this European observatory, EXOSAT, for anybody who remembers EXOSAT. But then when we had the next outburst in 2006, we had X-ray observations with SWIFT, the Rossi X-ray timing explorer. We had spectra from Chandra and XMM Newton. And in the most recent observation, again, we've had SWIFT, Chandra, and XMM Newton. So as time's gone by, we've been able to expand what we've been able to do at these different wave bands. And I'll just show you what the 1985 status was like. Apologize for the quality of this, but I just had to photograph them out of my PhD thesis, so they're a bit ropey. But the left-hand side shows you the low energy count rate. So in the EXOSAT instrument, there are relatively low energies, so less than about 1 kilo electron volt. And this is time after outburst on a logarithmic scale. And you can see this is the number this was the number of observations we had, whatever, 1, 2, 3, 4, 5, 6 observations there. And then there was a spectrum. We were able to get a very, this is how crude the spectra were at the time with EXOSAT. 55 days after the explosion, we were able to make a spectrum into the medium energy range, so above 1 keV into a few keV. And of course, you can fit models to that. You can measure the temperature of the gas and so on. So we developed a hydrodynamic model for the shock. We basically fitted it to this first epoch. So it fitted here, and then we just let the thing evolve hydrodynamically, and it does this. So it didn't fit very well with the observations that died, that the low energy fluxes died away quite rapidly. And so our solution at the time was to suggest that what was happening was the reason there was a decay was that because in any given explosion, the ejector expand from the white dwarf and they sweep away the red giant wind. The shock sweeps up the red giant wind and sweeps it out, so effectively creating a cavity. And then after the explosion, the red giant wind begins to fill that cavity again. So you can imagine that when the time comes for the next explosion, the red giant wind only extends to a certain radius. And so if you try and estimate where that is, our estimation was that the ejector reached the edge of the red giant wind at some point in here, somewhere between 70, 80 days or so after outburst. And at that point, then this thing sort of expands rapidly into the cavity from the previous explosion, and then everything cools adiabatically, and the X-ray emission drops away. So that was our proposal from 1985. It took till 2006 for the next explosion for us to actually understand what was going on. And these are the Swift observations. So we went from 6 epochs with Exosat to more than 350 epochs of X-ray observations with Swift. So when Swift's not doing gamma ray bursts, we can sneak in and do nova observations with Swift, and we continue to do that to this day. But we managed to get a significant number of sort of snapshot observations with Swift. And now you see something very interesting. There's pretty clearly two components to this emission, I would say. There's a component here that sits that sort of rises. We don't really have enough data here, but that's only a few days after the outburst, so it's hard to get data on this very rapid explosive phase. But it rises and then decays away, and actually we think continues right through here. And then sitting on top of it, there's another much brighter component that appears. It's very variable, and then it decays away, and then what's left behind is this thing that was there before. You can get a bit more information on that by looking at what's called the hardness ratio by X-ray astronomers. So effectively the spectral slope, so telling you whether the spectrum is dominated by high energy or low energy emission. And so this is the same light curve as you just saw on the previous diagram, except now it's plotted on a linear brightness scale here and a linear time scale. So this is this other component, the fainter component in here that carries on, and here's the bright component that sits on top. And the hardness ratio is plotted below. So where these data points are high, it's telling you that this is high energy or relatively high energy X-ray emission, and it shows you that this component in here, the bright component, is relatively low energy, softer in X-ray terms, which is superimposed. And then after that dies away, you go back to this relatively hard component again. So our current understanding of this now is that the harder component is what comes from the shock wave. So the shock wave traveling out through the red giant wind is producing the millions of degrees gas that produces this underlying emission. And then what happens is as that shock travels outwards, you gradually start to be able to see through the ejector, and you see down to the white dwarf itself where the explosion took place and where there's residual thermonuclear burning. And that's at a lower temperature, maybe a few 100,000 degrees. And that's what produces this soft emission. And there's this flailing about of this sort of rapid stuff here is something to do with the change in absorption through this sort of ejector curtain that then settles down. And then as the thermonuclear burning, as you run out of hydrogen fuel for the burning, this decays away, and then you're left just with this expanding hot gas that's left over in the red giant wind. And in terms of being able to prove myself, it's always good to prove your own PhD wrong, I think. Should be an aim for all scientists. Luckily, not all of my PhD was wrong, and luckily they didn't take it away from me. But if we superimpose, this is our Jan Uwe Ness here who did this plot, which superimposes the Exosat data points from 1985 on top of the Swift data, and you'll see this this is these are the Exosat LE data. Sorry, these triangles. So that's these data points where it dropped away like this. So this was day 55 after the explosion in 1985. So suitably scaled. This clearly, where we were thinking that what was happening was the shock was reaching the edge of the wind. In fact, it's the drop off in the soft component. So this completely separate component from the center. So that was particularly interesting discovery from 2006. I'm going to move on to radio now to show you a sort of development of what's been going on there. These are 1985 was the first radio observations of RS Oph. We had an interferometer between two of our big telescopes at Jodrell Bank, so a very short baseline interferometer. We also had some observations with the Very Large Array and a very early form of the European VLBI network, just a few telescopes running at that stage. By 2006, we got our network operating in the UK of radio telescopes on 200-kilometer baselines. We had VLA again. We had the full European VLBI network, and we also had VLBA in the USA. And in 2021, we added to that with we also have there's a telescope in the UK here called the Amy Large Array, Meerkat in South Africa, and also LOFAR, the low frequency array run out of the Netherlands. So in 1985, we had light curves looking like this. This is a flux density against time on a log-log scale in 1985, where it was detected at round about day 15 or 18 or something, rose and then decayed away. Initially optically thick as this source is expanding, that then becomes optically thin and then fades. In 2006, we were sort of ready for this. Of course, we had detected it in 1985. We got the reports that it had gone into outburst, and so handily working at a radio observatory, I was able to persuade colleagues to do some director's discretionary time observations. And this is 1, 2, 3, 4 or 5 days after the explosion. I have to admit that I wasn't necessarily expecting to detect this source, because if one naively took this radio light curve from 1985 and you sort of carried this thing down here, you might have expected the flux density to be way down here. But it was worth a try, and to start observing early, I thought. We did detect it, quite bright. And these observations here are the first 8 or 9 hours of observations, where we broke down one 10-hour run into individual sort of half-hour chunks. And within that time, you could see this thing rising rapidly. This is the next day or two later, again, still rising. Then it turns over, and then it maybe rises again and then joins back onto this curve. So there was something going on that we didn't expect, an early peak that we didn't know existed before. Again, when you look at the spectrum, you get a sort of complicated mix of thermal and non-thermal. Here's 2021. We've managed to push the observations earlier now. So again, from 2006, we weren't particularly expecting to detect it this early. Now in 2021, we are. And so we managed to get even earlier. And we were in, just over a day after the optical peak, and already detecting this thing going up into this rise. So one good thing to say about this is it's consistent from outburst to outburst, or relatively consistent from outburst to outburst. But also just illustrating this idea that you can learn from this previous explosion. The technology, the capabilities are all improved, and you can improve what you understand from it. That's a bit of a messy diagram, but it's just showing you by the time we got to 2021, we've got much wider frequency coverage, much more spectral information, and over a longer timescale, so allowing us in principle to try and understand how the source of this radio emission and how it's changing with time. Unfortunately, it is complicated, perhaps as you might expect, and it's a mix, as I say, of thermal radio emission and non-thermal radio emission, so synchrotron, presumably produced by particles, electrons accelerated in the shock. If we think about the imaging, so those were just flux density measurements. If you think about, we can make radio images, of course, at quite high resolution. Back in 1985, there was an image made with the early European VLBI network. It was sort of very, I suppose, quite controversial, actually, because it was pretty much a tour de force by colleagues like Richard Porkus and Richard Davis and people who produced this this image, but only with I think 3 telescopes. And so, you know, you're worried about the believability of some of these structures, and in particular, you know, the symmetry of this structure might be something you wouldn't be entirely sure about. But it looked like this two-sided, quite linear east-west structure. All the modeling I'd done in 1985 was all spherically symmetric. We really didn't have computers and things that were capable of doing much beyond spherical symmetry. If I picture, again, this is out of my thesis, I think, or this picture's out of my thesis. If I superimposed my spherically symmetric model on this radio image, this is where the shock would have been. The sort of outer shock in my model was about the same scale as the central component of the radio emission, which actually was, you know, satisfying, really. But clearly, we weren't really trying to understand what was going on out beyond this to the east and to the west. 2006, as I say, we had far better radio interferometers available to us. This is a VLBA image. I can still remember getting these data 14 days after the explosion, so a very rapid turnaround for a VLBI instrument. And getting the data in Jodrell Bank on a Friday evening, and there was a few of us sat around a computer terminal making this image. So people, I think Phil Diamond, who's now the director of SKA, was I think running the computer because he was the most familiar with VLBA at the time. And this sort of image appeared in the middle of the screen, and basically the exclamation was, "It's a ring." So this thing looks like a ring, very bright on one side, much brighter than the other side. But our assumption was that this could be mapped onto the shock wave. So the shock wave that's traveling out through the red giant wind, the binary system itself is very small on this scale. So you're not going to resolve the binary system at this distance. But you can measure brightness temperatures. You get 40 million degree brightness temperatures, so the non-thermal emission. It's the size of this. If this were the shock, and you know it's day 14, you can estimate shock velocities. You can estimate gas temperatures. You can compare that to the observed X-rays, and those things were consistent. So everything seemed pretty consistent with a model in which this is the shock wave accelerating particles producing synchrotron emission, but also hot gas producing thermal radio emissions. You get this sort of mix of stuff going on. That did indeed evolve into a linear structure. So it did start to expand east and west. This is a picture from a paper by Jenno Sokolowski and Michael Rupin and others that superimposes some VLBA and VLA imaging, showing you that there's something sticking out east and west on this structure. And just as a little movie here that Rob Bezic and I made with our Merlin observations over the first 100 days or so, showing you how it moves from being an unresolved point source to something that has extensions to the east and to the west. So in fact, that sort of pioneering observation made in 1985 that showed something sticking out east and west turned out to be real. Now, if we jump forward to 2021, so these are the most recent data. The top right is a combined E-Merlin and European VLBI network image from 34 days after the 2021 outburst, and that's it had been published in a paper by Ulisse Munari and others, 2022. And what you see here is this sort of relatively complex structure now that's sort of extended a bit east-west. And I just want to draw your attention. This is a European VLBI network image from the previous outburst from 2006 that we published from a similar time after the explosion, showing pretty much the same structure. So a bright feature here, which is bright here. Something it doesn't quite wrap round in this image. There's better data in the 2021 image, so something's wrapping around here, and also a component out to the east here, which is also visible here. So a similar structure. But I think what's particularly interesting about this is that by 2021 we have Gaia, and we now have not only an accurate distance to RS off, but also an accurate position and proper motion for the central system. And so Ulisse and colleagues were able to superimpose the Gaia position on this map. So here's the Gaia position where the cross is. It's quite close, but just off to the left of this bright component in the radio. And now I'm just going to go back to the 2000s. Here's the VLBI ring. Here's the Gaia position appropriate, precessed and the corrected for proper motion back to 2006 with the Gaia position. So it's pretty remarkable. One, that it's almost an identical sort of mapping onto this thing. And two, our assumption, which I think was reasonable at the time back in 2006, was that this was a ring and therefore the binary system was probably at the center. Clearly not the case. Clearly this initial structure that we see in the VLBI and then these other components appear to the east and west is offset from the binary. So what's going on? The proposal that we've made, the current working proposal, is that, and this is my little cartoon of it. So imagine the binary star system, the red giant and the white dwarf, oriented something like this. We've got a reasonable estimate of the tilt of the binary system relative to the line of sight, but it's on a very small scale. This is just showing you expanded out. So that binary star system is somewhere in here. And then if the wind from the red giant is sort of constrained to become more of a disk-like structure in the plane of the binary. So this is my crude cartoon of a disk-like structure. So it's denser in this disk-like phase. I mean, you may have come across lots of discussions of binary stars and winds, and you get spiral structures in there that run into each other, and you can produce these sorts of structures in the circumbinary material. Then when the outburst happens, the outburst from the white dwarf down on this small scale in here will find it most easy to expand in an east-west direction. So stuff's going to expand out more rapidly to the east and to the west. But you've also got some sort of asymmetry in the emission. So for example, one could imagine, and this is the next step for what I'm working on at the moment, is a simulation of this, that where this shock effectively is coming out of this side, this is where you're likely to see the brightest emission, just on the face of the disk that's facing towards you as the shock's breaking out through that side of the disk. And then a little bit later, you start to see stuff appearing coming out this side. And that's a sort of, I think a significant development of the ideas that we had back after the previous explosion. We've got a lot of data to put into that. These are all the E-Merlin images that we've been working on over the last year or two, showing this thing expanding with multiple components. We can measure the expansion rates So to the east, this is the western component, this is the eastern component with measurements of their positions against time, pretty strikingly linear from what we can see. Not really seen any evidence yet for this idea we had way back when of the cavity in the wind and things running off the end of the wind. The expansion velocity seems pretty constant that we can that we've been able to measure from that. But to be honest, there's quite a lot more work to be done there. And I just want to go on and just the last thing, just going to finish it with a little bit of the other sort of new thing from 2021 before I sum up, which is gamma ray observations. So in recent years, we've been managing to detect with Fermi in particular gamma ray flashes from novae, which we're pretty sure are a result of particle acceleration in the shock. So just like for some time now, we've been aware of the non-thermal radio emission generated from particle emission producing synchrotron. There also seems to be significant evidence that there's shocks, either shocks between the ejector and a pre-existing circumstellar medium like the red giant wind in the case of RS Oph, or in quite a few cases shocks within the ejector. So if there's variability in the speed at which material is ejected, then you get internal shocks in the ejector, and that can also, it seems, give rise to this gamma ray emission. And one of the very interesting things from 2021 was the HES2 detections and others of the Cherenkov flashes from high energy gamma rays. So these are producing these sort of faster than light per production effectively in the atmosphere. So they're seeing these gamma ray observations. Here's an example of Fermi. This is from Terry Chung and colleagues who've done most of the work with the Fermi nova observations. So you've got a very nice before and after picture with the galactic plane in gamma rays, and here's after. See how bright RS Oph is in gamma rays in the gamma ray sky, and here's the HES detection in high energy gamma rays. So now in the gamma ray community have these spectral observations. So they've got, there's only two epochs here after this is 2021, 9th of August and 13th of August. And you see the Fermi spectrum, but also you can now add on these higher energy HES data, which basically their proposal is that it's actually proton acceleration in the shock. So rather than say electron acceleration in the case of the synchrotron radio, they're getting proton acceleration in the shock wave. So this is this is a lovely artist's impression, by the way. It's much better than my cartoon from earlier. But the binary star system, I mean, I think I would draw the binary star system on a smaller scale in here, but there's the red giant, I think, and the white dwarf's probably in here, is in the middle, oriented with the plane of the binary. It's actually at an angle of, 50 degrees or so to the line of sight, but oriented sort of vertically roughly. And then you get these sort of bubbles produced by the shock that expand out east and west. This is the red giant wind, this red stuff that's a sort of disky, it's more in the plane of the binary system than it is perpendicular to that plane. So that's the disk in the plane of the binary system. The explosion drives a shock wave through the wind, which escapes most easily above and below. Shock wave heats the wind to millions of degrees. That produces the X-rays and the thermal radio emission. That shock accelerates electrons, producing the non-thermal radio emission. It also accelerates protons to relativistic speeds, which basically, upon an interaction with those relativistic protons crashing into nuclei in the wind, produce the pions, which then decay and produce the gamma rays that Fermi and HES are seeing. That's the gamma ray community's proposal for those detections. So I think just my last slide, the end for now. Can we produce a detailed physical model? I think we've done we made various models over the years, but I think there's significantly more data now as a result of 2021, and I think what was really was particularly useful was to have that Gaia position just to change our perspective on the thinking of this, which I think will be particularly helpful. So we need to work on that modeling aspect of things. That'll hopefully help us understand some of the details about what are the different radio emission components we see. Is the ejection collimated by this red giant wind distribution? Could it be intrinsic to the explosion itself? How does that, in that sense, how does that link to the binary? How does that link to the evolution of the binary and the accretion? There's a lot of stuff to be done on particle acceleration, I think, in these systems for anybody who's interested in particle acceleration, because we've got real-time observations of how these things evolve, how the spectra evolve, how the fluxes evolve, and I think that could be particularly interesting. And then, finally, this sort of question of the type 1a supernova progenitor stuff. One thing we would need to understand there is whether these things can pin down the amount of mass that's ejected, compare that to the estimates of the amount of mass accreted, and find out whether, if more mass is accreted in the period between outbursts than is ejected, then that would imply that the white dwarf is growing in mass, and hence these high mass white dwarf systems are moving towards the Chandrasekhar limit, and we really are not completely sure of the answer to that. Well, we're not sure of the answer to that question yet, so that's a big one to look at. So I think that's about me finished, and I do hope. I mean, I'm 60 years old now, and I've been observing this thing for nearly 40 years, I suppose. And I've probably got another outburst or two in me. Let's hope. But I hope you've enjoyed hearing more about it, and I'm happy to take any questions.
Thank you very much, Tim. Wonderful talk. Now it's time for some questions. Anybody has a question? Alessandro?
Tim, I would have several, but I'll just stick to two, just for the sake of just to leave time to other people. So I guess the easiest question is, how transferable is the modeling you just showed to classical novae? So when you don't have a wind, you have a L1 overflow and blah.
So I think the answer to that is well, the biggest difference is that I mean, apologies for people who aren't sort of experts in this area. There's a lot of names of different types of system. So you hear about things called symbiotic novae as well. So they're white dwarf systems that have a red giant in the system as well. And they occasionally have these explosions on the white dwarf that are nova-like outbursts. Symbiotic just means they show an example of a hot component in the system, which is the white dwarf, and a cool component, which turns out to be the red giant. So I think the difference is whether there's a red giant or not, because if there's a red giant, there's almost certainly a fairly dense circumstellar medium for the ejector to run into. And once the ejector run into a circumstellar medium, then you get a much stronger shock system set up, and that, therefore they behave somewhat differently. Certainly, their observed properties will be different. But I did briefly mention towards the end that we do see. I mean, we've always said way back to, there was a nova in 1991 called Nova Herculis, V838 Her, which we detected with ROSAT. People remember ROSAT, the Röntgen satellite, X-ray satellite, and we detected that in just a few days after the explosion, and it showed evidence for hot gas. It was, a hot gas spectrum in the X-ray, and so up to that point, these classical novae which are the ones that we only see one explosion from, and which generally don't have red giants. They tend to have low mass main sequence stars as their secondary component, therefore no real significant circumstellar medium to speak of. People weren't expecting to see the hot gas, the shocked gas. They were expecting to see a hot white dwarf. And what we saw was these X-rays from hot gas. So our proposal at that time was that every nova should basically show evidence for both a hot white dwarf and shock heated gas. And what would change from one to the other was the relative amounts that you see. So in a case where there either wasn't really a significant circumstellar medium, in which case you don't have this external shock to produce the hot gas, the amount of shock heated gas you would see would be reduced, but you would still have the hot white dwarf. In cases where you had circumstellar media, you get a lot more hot shock heated gas, like in RS Oph, so that comes right up. We failed at that point to predict that what we saw in 2006, which is that we'd see the hot gas, but then we'd see through it and we'd see the hot white dwarf later. We completely should have predicted that and didn't. But then in the classical novae, like this Nova Hercules in 1991, which doesn't have the circumstellar medium, so you wouldn't have expected, people weren't expecting the shock heated gas, but we actually saw it earlier on. Clearly what then happens is that the mass when it's ejected isn't ejected all at a constant rate, and there are variations in the mass loss rate. And once you put those into your models, which we have done, you get intra-ejector shocks. And there are models like this in gamma ray burst systems as well, to be honest. So you get these intra-ejector shocks, which can also produce the shock heated gas. But it's not as dramatic as it would be in something like RS Oph. And the gamma ray observations also confirm that we see gamma ray detections even in simple classical nova systems with main sequence dwarf companions. So I don't know whether that's quite a long answer to your question, I'm afraid, but I hope it gives you some. So the modeling is, it's all, basically you can apply similar models. It's just how much external gas you put in there for things to run into, and how much intra-ejector variation you put in to produce shocks within the ejector.
That's another one. I wanted to ping you on the last point of your conclusion of the Type 1a supernova thing. I remember in the Kiel conference in, where was it, 2007? That there was a voting if RS Oph would end up as a Type 1a or not. So I honestly don't remember the result. But after yet another explosion, what is your feeling? Not sure if we should stop the recording so that it doesn't get.
I don't think my feeling. I don't think I'll be put in jail for the wrong feeling. I'm quite by nature, I'm quite a cautious person. I'm not the sort of person who, like the British Prime Minister, puts bets of £1,000 on refugees. I don't know whether anyone's watching the news, but anyway, there was controversy here about our Prime Minister betting his own money on his own politics. But anyway, I don't think I put my own money on RS Oph being a Type 1a supernova. I think the problem is we have no current evidence, I don't believe. And I say that knowing that just the other day, I think I spotted something on Astrophysics that was a title of a paper that I remember on a dynamical model of something, and I thought, I really ought to read that paper. So I'm going to say this without having read the paper, because one of the measuring how much mass is ejected and how much mass is accreted is the key measurement to make here. And though both those things are really hard to do, and people have tried to do them in different ways over the years, and I don't think anybody has come up with a convincing answer to that. I don't think we have a convincing number Now there are things you can do. If you can measure the properties of the binary system before and after the explosion, the orbital system, and hope to measure the change in mass. And people have tried to do that. And I must admit I can't tell you right now the numbers on that because it's a while since I've looked at those things. But that's been done a few times with T-Pix maybe, and maybe others. And I think maybe this paper I just spotted the other day was another similar example. So I ought to be a bit careful. I'm going to have to sit on the fence because I don't know. And I think it's an unknown question. And I think someone correct me if somebody there's more of an expert on type 1a supernova than me, but I don't believe we're sure what the progenitors are, whether they are. There's almost certainly, my guess is there would be at least two classes of progenitor, and some of them would be the symbiotic nova type systems, and some of them would be the double degenerate, the white dwarf collision type systems. And it's to do, you can do things like look at the presence of hydrogen in the spectra post outburst. That might give you an idea as to what's going on. And it certainly looks like some type 1a supernovae don't show any evidence for being a symbiotic type system. But I'm afraid I don't know what I did in 2007. I don't remember the vote. I may not have put my hand up because I'm not putting my hand up now either. I'm too cautious, but that because I think these crucial measurements are too hard. They're just very hard to do, and they're very model dependent.
Yeah.
Which is why, right at the top, where I say, can we produce a detailed physical model? I think we're inching towards a complete model of these systems. I think we're almost there, really, because we've got such wide spectral coverage now, such good time coverage now. We really ought to be able to pin this down, I think. And I'm not saying I'm the person that's capable of doing this, actually, but someone ought to be able to pull all these things together. I don't know much about particle acceleration, for example, and any work I've done on that has all been quite simple-minded, rather than a proper sort of approach to particle acceleration. It's more of an equipartition type argument. But I think if we were to combine forces on that, we could make a lot of progress before the next explosion. Give us another 15 years and we'll make progress. Come back to me when I'm 75.
I will. Okay, next question by Mohammed.
Okay, thank you very much for the very nice talk. So I'm not a professional in time domain or stellar astrophysics, but one thing caught my eye when I saw the AAVSO plot that showed the time of the of the shoots. So over there, they weren't equally spaced, right? So some of them were more had more years, some of them had less. So does that variation in the repetition cause? Can that be included in the models, or is it included? I didn't hear. Maybe I missed it. If you included this different variation, so it's not repeated.
So yeah, you're right. They're clearly not. They're not completely periodic. So the shortest known inter-outburst timescale is 9 years, which is this one here, 1958 to 67. But then this is really a long one here, which is what some people have suggested. Can you hear me? Okay. Yeah. And so some people have suggested there might be another one in here, but again, I mean, in a way, that comes back to the answer to that last question, which is that what's going on there. Well, probably the accretion process isn't completely smooth. So probably, we might assume some sort of accretion rate of solar masses per year from the system, but that isn't going to. It's probably got some variability in there. You can see there's something. There's very intrinsic variability in the quiescent brightness of this thing. It's not a particularly elliptical orbit, so it's not like it. It's those elliptical orbit variations that are producing the variability, we don't think. But it's probably just intrinsically variable in terms of the accretion. We're not how that material flows through an accretion disk and ends up on the surface of the white dwarf, and exactly when or where that's triggered, that's a whole massive area in itself, right? People have done some calculations of that as to whether, you know, you trigger it at a single point. The group in Israel particularly have done some calculations, and then that thermonuclear runaway seems to progress very rapidly around the surface. But whether that's got all the physics in there or not, we're not sure. You know, it's a really, I mean, I think it's really interesting because of the range of physics you have to put in. But you can certainly put, and in fact I did, even way back in 1985. Don't want to hark on about my PhD thesis, but at the end of that thesis, after that, I did actually do some simulations where I put in these different inter-outburst timescales, because of course, if the end of the wind, reaching the end of the wind was an issue, which now I'm not so sure because of what we've been seeing in 2021, where this expansion velocity stayed constant, seems to have stayed constant. But if it did, then you would there wouldn't be much wind built up in this time, and so a 1967 explosion would reach the end of the wind quicker than, say, a 1985 explosion. What we proposed then was that there would be interactions between outbursts, multiple outbursts, and in fact that's what this paper here that this picture's from is for the most rapidly recurring nova. So this is in M31 in the Andromeda galaxy, and the nova's sort of in the middle of here, and this sort of structure in here was detected. So this goes off every year, was discovered in 2008. It's a bit distant to get good data on, right? That's the problem. It's not in our galaxy. But this massive structure was developed. So we did produce a paper on this back in 2019, where we did a whole bunch of simulations of many outbursts. So thousands and thousands of outbursts. And basically you sweep up the interstellar medium, and these new ejections keep running into the back of the old material, and you basically build structures of this sort of scale. So we thought that was an interesting proposal. So exactly how that works, yeah, we do think about it, and but yeah, it's probably the variable accretion process, I'm afraid, and it's another bit of messiness that makes answering some of those important questions very hard.
I have a question about the fluctuations in the X-ray light curve. I think it was the 2006, the soft X-ray component that had this large variability in amplitude.
Yeah.
When the light curve was rising. Is that related to changes in the opacity?
I'll just show you the picture. So it's these fluctuations here, and they're extremely rapid, and they were a bit of a shock. So, sorry, they're not a shock. This is the shock down here. So this is just the variability in the by huge, you know, a huge range in here from observation to observation. They've been a real conundrum. Now, I ought to know a better answer to this, right? But it's a couple of years since I read the paper, and my memory is not as good as it used to be. Our assumption has always been that it must be to do with the opacity varying, but back in 2006, a simple approach to modeling that wasn't completely consistent with the temperatures and the brightnesses. So we didn't really bottom that out. We didn't really answer that question completely in 2006. I think the 2021 data, there's been a better analysis, and probably, I think do you know Jan Uwe Ness? He's I haven't referenced. So Jan Uwe had this paper from, but I've probably not cited the paper from 2021. I just didn't have time to put it in here. There is a paper from the 2021 explosion that I think returns to that question, and I think the conclusion was that they're now pretty sure that that is opacity variations. So as the material, these shock systems that are also cooling can be quite unstable, and so the ejector can break up into clumps. There's instabilities that occur in there, and they clump up. You remember the old optical pictures I showed you with a very clumpy emission. So this stuff breaks up into very clumpy material, and the line of sight then can be quite variable, we think, in terms of the absorption.
They disappear after the peak because the bubble expands and then the material is not optically thick anymore.
Yes, exactly. Yeah. And you're effectively seeing through a much more, as this thing expands with all these little clumpy bits in there, the densities are going to go down intrinsically, but just along the line of sight, I don't think you get as much variability actually as when things are all, much more, much closer in. So we think that's the explanation. There are periodicities in the X-ray light curve. There's very short timescale periodicities actually, which I'm not sure there's a good answer to what those are now, whether it's a question of whether it's an instability in a periodic instability in the nuclear burning rate or a pulsational instability on the white dwarf. But that's not what this is. This is much more random. So almost certainly to do with absorption in the overlying ejector.
Okay. More questions? Okay. Thanks again, Tim.
No problem. It's great to see you all, and
we hope to see you here sometime if you pass nearby.
If I'm passing by, I should
let us know.
Yeah, I should stop off. We should take our camper van and go around Spain. We've done that, but we've only got as far as the Pyrenees, I'm afraid. We didn't go any farther south. So, but it's a lovely place to visit. So I'm sure I'll pop by if I can. I looked at you on Street View. I thought, where are you? And you're in some lovely square.
Yeah.
You can actually take a ferry to Santander and then from Santander come down.
That's what we did. We took our camper van in the ferry to one year we went to Santander, and the next year we went to Bilbao, but then we tended to just circle around the Pyrenees and we then drive back up through France and come back the short way. But yeah, we should stay down the bottom end where it's warmer probably than it is here. Great to see you anyway. Thank you for inviting me.
Bye, Tim.
Yeah, cheers. Thank you. Good to see you. Thanks, Alessandro.
Cheers.
I'll answer all these questions in my next seminar for you. Bye.
Thank you very much.